Hello everybody and welcome to another geometry lesson. Today, section 2.3. Section 2.3 is all about learning more postulates. Now, what is a postulate? Well, we actually learned it all the way back in Unit 1. A postulate is another name for a statement that we can take as a fact, or sometimes a statement that might seem obvious to some people. There are 7 postulates that we're going to be talking about today. The first one is called the two-point postulate. And we mathematicians are not very creative with our names. So believe it or not, the two-point postulate starts off with the following. Through any 2 points, there exists exactly one line. So, if you have 2 points, then you are allowed to and encouraged to draw a line through them. That's basically all it means. In fact, that's a fact that we talked about all the way back in Unit 1 as well. So, the way that we would write this, or maybe the way we would see it most likely, is if you just have 2 points sitting around, I'll call these points A and B, then we can assume that through A and B, we may draw a straight line, just like that. That is the two-point postulate figured out. So far, not so bad. They will get a little bit more complex, but I don't think they go too much further than this. For instance, the line-point postulate is the same thing, except it's the converse. It's backwards. The line-point postulate says a line contains at least 2 points. Wait, Mr. Strager, isn't that the exact same thing? Oh, I forgot to label my line. I'll call it line L. It is very similar, but it is not the exact same. The difference is what we are given at the start. We are told that a line contains at least 2 points. So this postulate tells us if you ever have just a blank line, we'll call it line L, then you are allowed to create at least 2 points along line L. Do you see the difference now? They both end the same way, with 2 points on a line, but they start differently. In the first one, we're given 2 points. In the second one, we are only given a line. Next up, we have the line intersection postulate. And again, we mathematicians, not being the most creative namers in the world, decided that it's exactly what it sounds like. If 2 lines intersect, and remember, intersect means to cross over. So either they cross like this, or whatever may have you. Then their intersection, the place where they cross over, is exactly 1 point. This time, we're dealing with 2 lines at the very start, and we have the other condition that those lines have to be crossing. So I'm going to make 2 just random crossing lines. No reason why I made them like this. I'm going to call them M. I'm going to call them N. Again, we use cursive lettering to notate lines. Then their intersection, the place where the two of them cross, is just 1 point. The exception to this is when the lines are on top of each other, but if the lines were on top of each other, then we would even notate them differently as well. So then lines N and M intersect at point P. This one here doesn't really have a converse. It doesn't say if you have a point, then you can make two lines through it, just because that fact is something you can do with any figure. You can draw two random lines through anything. The 3-point postulate is where we start going into the second dimension. When I say going into the second dimension, I mean we are dealing with planes. So the 3-point postulate is through any three non-collinear points there exists exactly one plane. Ooh. What on earth do we mean when we say non-collinear? Well, non-collinear just means they can't all three of them be in a perfectly straight line. At least one of them has to be off of that straight line from the other two. So, if we're starting with just the information that, hey, 3 points exist, these two would be collinear, this third one would not be collinear with them because they don't all three form a straight line. I'll call it X, Y, Z. If those 3 points exist, then there is a plane that is created around those 3 points. Here's how we would draw it. We would have X, Y, Z here, and to show that they are all three on a plane, we would draw a parallelogram like this, and I'll call it plane M. Next up, we have the plane point postulate. And just like how the 2-point postulate and the line point postulate are converses of each other, the plane point postulate is a converse of the 3-point postulate. It says that a plane, so if we start with a plane, it contains at least 3 non-collinear points. So if I start off with my shape like this, I'll call it plane M. Forgot the word if, sorry. If plane M exists, then we can create 3 unique and non-collinear points on plane M. Again, I'll call them X, Y, and Z so we can compare the two. Done. These two are now handled. This one starts with 3 points and says you're allowed to make a plane around them. This one starts with a plane and says you're allowed to put 3 points on it. Next up, we have the plane line postulate. And the plane line postulate is the toughest of the 7 because there are a lot of things happening all at once. So listen. If 2 points, so again, we're going back to dealing with points, lie in a plane, and I'm actually going to start off by drawing these 2 points in a plane. It'll be a lot easier down the line to see it happen. If 2 points, I'll call them, I don't know, C and D, lie in a plane. So I'm going to call this plane plane M once again, just for consistency's sake. Then, and that is also the then that goes into the definition, then the line connecting them also lies on the plane. In other words, if you've got 2 points on a plane like this, and you connect them with a line, that line is also going to be on the same plane as the points. And that's not crazy to understand. I mean, we understand that if I draw a line on a flat piece of paper, then it's still on the paper. But the way that it's worded makes it very difficult for us to piece together. This is the only postulate that contains lines, points, and planes. Last but not least, we have the plane intersection postulate, which is kind of like the line intersection postulate. The plane intersection postulate says, if 2 planes intersect, then their intersection is a line. Oops, forgot to color code that. It will be a line. So this time, when 2 planes crossed, it makes a line. Let's see this in action. To draw this out, to draw 2 planes intersecting, here is my suggestion, because it's kind of hard to visualize. Start off by drawing 3/4 of a plane that's basically horizontal, like this is a plane that we were portraying as being flat and going from side to side. Then, going through it, draw 3/4 of a plane that's going vertical. This we can imagine as a piece of paper standing on its end. It should look like 2 staples almost crossing. To finish the drawing, anytime the plane does not go past a plane, or anytime one plane does not go past the other, you make a solid line. Anytime it goes past it, you make dotted lines. So here we have the purple one. It goes here. Oh, got to make some dotted lines as it's going through the plane. And then a solid line on the other end. You can imagine this as 2 pieces of paper that are crossing perpendicular to each other. If you have that situation happening, then, well, the first thing that happens then is that Mr. Strager will be able to draw it a little bit better, gets a second try. But what ends up happening in terms of what's on these is the following. Again, I'm going to draw them out. You would think that with a second try I'd get this one better, but unfortunately drawing these planes is not easy business. And then there we have the dotted lines going down. Then, what we can say is, there are a couple places where these planes intersect. I mean, we literally see them cross here. We literally see them cross here. Through those 2 points, there is a line. So there's a line that goes through both those pieces of paper, or both of those planes. And of course, I want to label our planes. I'll label them M and Q, M and Q, and I'll call this line, line L. Easy enough, right? Let's take a look at example 1. This one is just asking you to regurgitate which example is which. So this says, if you have 2 lines that are crossing, then where they cross, there is a point. That one we would just cite as being the line intersection postulate. And these 2 planes, if 2 planes are crossing, then there is a line between them. We just did that one. That was the plane intersection postulate. These names and these words will be used time and time again. So please, commit at least the names of the postulates to memory, and maybe some examples too, just so you understand what we mean when we say them. Let's flip to the back. Now, This may be one of my favorite diagrams in all of geometry. Why, Mr. Strager? It doesn't look that interesting. It just looks like a lot of planes, a lot of lines, and a lot of points. Well, I'll have you know that this diagram contains examples of every single one of our postulates. Yes, indeed. Don't believe me? Let me give you an example. Let's take a look and say I wanted to find an example of the 2-point postulate. The 2-point postulate, as a reminder, says if you have 2 points, then you can create a line that goes through them. On this diagram, do we see 2 points that have a line that goes through them? Why, yes, indeed we do. Through points B and A, we have this line, which we've been given the name N. So, for the 2-point postulate, we would write out through points A and B, there exists line N. Fantastic. I would like you to try and see if you can find 2 other postulates in this diagram, just as a warm-up. Again, all 7 of them are there, so I will be able to talk about all 7 of them with you. Pause the video here and see if you can find examples of all 7 postulates. Go. How'd you do? Let's take a look at some of these postulates. The line point postulate says that line N, blue, contains points A and B. The line intersection postulate tells us that lines M and N intersect at point A. The 3-point postulate says that through points A, B, and C, there exists a plane, and that plane that has all 3 of them on it happens to be P. Don't be fooled, plane Q only has A and B, C is on the different one. The plane point postulate is the opposite, which says that plane P contains points A, B, and C. The plane line postulate, let me fold my paper so it's easier to see, says that points A and B are on plane P. So line N is also on plane P. That was a tough one. And the plane intersection postulate says planes P and Q intersect to form line M. Line M is the one that goes through both. So, how'd we do? There is one more property that I want to share with you. It's not really a full postulate, but it is something we should keep note of. A line is a line perpendicular to a plane if and only if the line intersects the plane at a point and is perpendicular to every line in the plane that intersects it at that point. That's an incredibly wordy, incredibly long explanation. It's an explanation, though, that I think would be even better if I showed it. So, give me a moment to turn my camera. I will unpause in a moment. So everybody, first off, this is now a vlog channel. Here we see a line on a piece of paper, specifically the piece of paper we just did the example in. Sorry about that. Here we have a line that is on a flat piece of paper, and we recognize that a flat piece of paper is just like a plane. It's a flat surface where a line is on. This here is a very sharp line. If I have a line that crosses through the plane, like so, and it crosses through that line, what type of angle is formed between the plane and the line? Well, it's a perfect right angle. It's a 90-degree angle. we can imagine that this here intersects this here at a right angle. So that's all that means. A line that is perpendicular to a plane at a point is perpendicular to other lines on that plane. So that's enough of the Mr. Strager's face jump scare moment. Let's take a look at example 3. We want to show a diagram of line TV intersecting line segment PQ at point W so that TW is congruent to WV. That is an insane amount of words in one spot. So let's digest it one piece at a time. The only way to eat your way out of a prison made of cake is one bite at a time. We want to start with line TV, right? Line TV is going to be this line here. And it intersects, so it crosses through line segment PQ. So I'm going to make a shorter line segment. Doesn't need to be shorter. But I'm going to label it PQ. The name of the point where it crosses at is W. So this big old red point is point W. Already it's a little congested. The only thing is, we want TW, this green point to the red point, to be congruent to WV. So how do we show that those two are the exact same length, that they're congruent? We've got to put some congruency marks. This would be a diagram for example 3. Example 4, we've got another complicated diagram. This time, it's two planes crossing at a different angle with a lot more lines on it. We want to figure out which cannot be assumed from the diagram. It's not that it's blatantly false, it's just that it cannot be assumed based on what we see. So pause the video and see if you can determine if these are true or false. Hopefully you've had a chance to try it out. Let's see. First off, we absolutely can assume that A, B, and F are collinear because they are literally on the same line. That's the definition of collinear. But can the same be said of E, B, and D? I mean, they certainly look like they're on a straight line, like E to B to D. It looks like it'd be a straight line. But if there's no line there, we cannot make that assumption. Maybe point D is 1 millimeter off of that line. Our eyes wouldn't really be able to tell it. So we cannot assume that points E, B, and D are collinear. Line AB is supposed to be perpendicular to plane S. That one is absolutely true because we have a right angle marking here. It's sort of faint to see, but that right angle marking says from AB down to plane S is a right angle, so it is perpendicular. True. The same can't be said for line CD and plane T. There's no congruency, or sorry, not congruency. There's no right angle marking there, so we can't assume it's at a right angle. In fact, just looking at it, it looks like it's a little bit tilted, so it looks like it's not quite at a 9 degrees. That is false. Finally, we want to see if line AF intersects line BC at point B. Line BC is here, AF is here. The crossing point is point B, so that would be true. So there we go. That concludes our notes for today, everybody. Thank you so much for listening, and have a fantastic rest of your day.